second session of today. So now we have the talk of Maria Carolina de Aguiar from Federal University of Minas Gerais, and she's going to tell us about Raman response of cuprates. Thank you, Carolina. The floor is yours.
Okay, thank you, Thais. So I would like first to thank the organizers for the opportunity to give this talk. Here's the outline that I will follow. Indeed, there are spoilers on the conclusions that I will try to convince you we can see from our results. So I will start by giving a brief introduction about copper oxide superconductors or cuprates. Then I will show you results we got for the pseudo-gap phase. In the first work, we saw that the pseudo-gap phase ends at the same doping at which the firm surface changes from being hole-like to electron-like. This is a Lifshitz transition, and more recently, we looked at these Lifshitz transitions and saw that its nature changes from being continuous to discontinuous as the pseudo-gap phase emerges. So when we do not have the pseudo-gap phase, the transition is continuous, while when we do have it, it is discontinuous. Then I will talk a little bit about the charge density wave phase of the cuprate phase diagram. And then I will show to you that the B2D Raman response shows a deep hump feature, which is a signature of this CDW phase. And the energy scale related to the CDW, it depends on doping at the same way the pseudo-gap phase does. All these results, the theoretical results that we got, were motivated by experimental results obtained with Raman. So I will all the time show first our motivations, and then the experimental motivation, and then our theoretical results. Okay, just to start, here we have the structure of a given cuprate superconductor. We can see that the copper and the oxygen form planes, and the other atoms act as charge reservoirs. So when treating this compound theoretically, we will consider a two-dimensional model representing the copper oxide planes. Superconductivity emerges when we dope a multi-insulator. We can see here the phase diagram, temperature as a function of doping. If we do not have doping, we have 1 free electron per copper atom, and this corresponds to a multi-insulator. It is when we dope the system that we see the superconducting phase. I will not show results for the superconducting phase, which is not well understood. The origin of it is not yet well understood in the literature. I will talk about these other two phases, the pseudo-gap phase and the CDW phase, which also there are things we do not understand. So what is the pseudo-gap phase? In this phase, we have a suppression of spectral weight in certain regions of the Brillouin zone. So we can see this by looking to angle resolved photoemission spectroscopy. So we have an example over here. This is ARP's intensity as a function of energy. If we look at the nodal region, which corresponds to the diagonal in the Brillouin zone in K space, we see a peak here around the firm energy, right? This is characteristic of a metal. But if we move to the antinodal region of K space, then we see a depression. We see a suppression of spectral weight close to the firm energy. And so the system as a whole is a metal, but we have this chain of behavior along the K space, and this characterizes the pseudo-gap phase. What about the charge density wave? In the charge density wave, we have a tendency of electrons to segregate into periodically modulated structures. Here we have a resonance X-ray scattering result. This is the intensity as a function of 8 in two directions. This is in K space, and we have two different directions in K space. The authors of this reference concluded that these results, these experimental results, are compatible with having a modulation in charge. As we can see here, this is the charge density in the real space, and there is a modulation in it, which is corresponds to 3.777 times the lattice spacing. right? It corresponds to these spots where the bright spots. They did a Fourier transform of this figure over here, and these are the results that they got in K space. The green symbols here in the first plot, it corresponds to this direction, where there are points in the when they do the Fourier transform of their model to describe the system, right? While the red or orange one, this one, there are no points in this direction. So they conclude that this modulation in chart is compatible with what they see experimentally. Okay, so this was my brief introduction about cuprates. I will start talking about things related to our works. In the first one, we saw a relationship between the pseudogap phase and the firm surface topology. As I said, I will motivate our works by looking at the results gotten from Raman experiments. So briefly, in a Raman measurements, this is what they do, the experimentalists do. They shine light into a sample. An electron is promoted from this state to an excited state. It then decays, and there is some scattering light. And there is a difference in energy between the initial state and the final state. These measurements can be done using different polarizations of light. There is the BU1D polarization. It corresponds to these vectors over here in real space. And in K space, it corresponds to probing the antinodal region, where we see suppression of spectral weight in the pseudogap phase. They can also use this polarization of light, which corresponds to B2D. And then when we go to K space, we are probing this region of the K space, right? So I will show you results for the BU1D symmetry when I want to describe the pseudogap phase. And we will see that for describing the CDW, or for looking at signatures coming from the CDW, we will need to look at the B2D polarization of light. Okay, here are the results, the first ones. So let's look first to left here. This is loss of spectral weight. It corresponds to these stars over here. When it is finite, we have the pseudogap phase, and when it goes to zero, there's no pseudogap phase anymore. So this doping here, this is loss of spectral weight as a function of doping. So when this stars goes to zero, it means that it's the doping at which the pseudogap phase ends, right? Now let's look what they got for the Raman response. This is the integrated Raman response, and it's a ratio between the intensity in the B1D and the B2D polarizations of light. Now they got these results over here. There is a maximum coinciding with the doping at which the pseudogap phase ends. They did a simple tight bind model and got to the conclusion that the doping P star at which the pseudogap phase coincides, the pseudogap phase ends, coincides with the doping at which the firm surface changes from being Hawley-like to electron-like, which corresponds to a Lifshitz transition. And I will show you that indeed we got the same coincidence in our theoretical work. So theoretically, what we did, we solved the Hubbard model in 2 dimensions. Here's the Hamiltonian for it. So C destroys an electron, and C dagger creates an electron, and T is the hopping amplitude. So when we sum over all the lattice sites, this term here corresponds to the kinetic energy. Then we consider electron-electron interaction, U, when we have 2 electrons at the same site. So it's I here and I here, and they have to have opposite spins due to Pauli principle. The last term, mu, is how we set the doping, right? We change mu to change the doping of the system. We will study the normal state, that means the non-superconducting phase. This model was written in a 2-dimensional space. And to solve it, we use cluster dynamical mean field theory. I will show you results as a function of doping. And we have a fixed T prime, which is the hopping between second neighbors. Okay, just one slide to summarize cluster DMFT. So our original model is a one in a lattice, right? It's a difficult problem because we have interaction in all sites. We map this problem into a cluster of sites. And this cluster of sites is connected to a bath of non-interacting electrons. So the advantage is that now we have interaction only in the cluster sites. We do not have interactions in the bath. This is done in a self-consistent way. Here's the phase diagram that we got to that model. This was a work done by Helena Bragança when she was my PhD student in collaboration with Shiro Sakai and Marcello Tivelli. So this is the phase diagram, interaction as a function of doping. If we do not have doping, then we have a metal insulator transition, right? This is the Mott insulator, corresponds to this blue line. For small values of U, we have two phases over here, a correlated firm metal and the pseudo-gap phase. The ground state, the smallest solution, the solution with smallest energy is the correlated firm metal, okay? And when we increase EU, then the pseudo-gap phase gets a stable solution. And the pseudo-gap phase ends at this P star given by this dashed line over here. If we look at the spectral weight, in K space, so this is Ky, Kx, at zero frequency, close to the firm energy. This is what is given here as in colors, right? And we see that blue corresponds to reduction in spectral weight. So we see this suppression of spectral weight at the anternodal region as expected for the pseudo-gap phase. I don't know if I told it before, the U parameter relevant for cuprates is high U, so it's this region over here. And indeed, if we compare these results that we got for the spectral function at the firm level with ARP's results, we have a good agreement between theory and experiments. If we now move to higher values of doping, this is what we get for the spectral function. We see that the spectral function is finite at the anternodal region. We can think that we can define the firm surface by looking at the maximum of the spectral weight at the firm level. So we can see that the maximum here, or the topology coming from the maximum, changes a lot when we go from small doping to high doping, and this corresponds to the Lifshitz transition that I mentioned before. So in this case, for small doping, we have a hole-like firm surface, and for high doping, we have an electron-like firm surface. And I should call your attention, so this doping where we see this transition between hole-like and firm-like firm surface corresponds to this red line over here, this PLT from Lifshitz transition, and we see a coincidence between P star and PLT for larger values of U. And this is in agreement with the experiments that I showed to you a couple of slides ago. And we can also see this other plot where there are a couple of cuprates. Here, this is P star, the doping at which the pseudo-gap phase ends, and PFS for firm surface, which coincides with PLTs, is the same definition, right? And we can see that all these compounds come here along the diagonal where P star is equal to PFS. So our theoretical results given in this phase diagram are in agreement with the experiments. Although I was showing you Raman experiments, in this first work we were not calculating the Raman response, but we did it more recently. I should submit the paper next week to archive. And here are the results that motivated our work. So this chi double prime is the quantity that the experimentalists get in the lab. They divide this quantity by the frequency. They integrate up to a cutoff, and they call this chi-0. This chi-0 is related to a static electronic nematic susceptibility. This nematicity is related to a broken rotational symmetry in the CuO2 plane. Here are the results for chi-0, so this quantity over here, as a function of temperature and a couple of samples. We are interested in a region of temperature here above the critical temperature where we see the superconducting phase, right? For these three first samples here, we have P is larger than P star, so we are in this region of the phase diagram. And for these other three samples, we have P smaller than P star, so we are in the situation where the pseudo-gap phase is observed. If we fix the temperature, say at 100 Kelvin, to be above here, above the superconducting dome, we see that we have a non-monotonic behavior. So we go from the blue, so as we move along the samples here, we are decreasing P. We are doing like this in the phase diagram. So we go from blue to red, to magenta, to green, to orange, and finally pink. So we have a non-monotonic behavior over there. Okay, so these were the experiments. Now, how do I calculate the Raman response? So I use this expression over here. We have the product of two Green's function calculated at different frequencies. This is compatible with the fact that in the experiments we have an incident frequency here and I scattered the light with another frequency over here, right? So that's why we have different frequencies in the eight Green's function. This gamma is the Raman factor. It is related to the polarization of light. So it will differ whether we are calculating the B1D response or the B2D response. We do the calculation on the imaginary axis because it is more stable to do so. And this quantity here on the imaginary axis is related to the experimental one in the real axis through a chronic relation, which is given by this equation over here. In particular, if we look to the limit where I omega goes to 0, and that's what I'm going to show you, this limit always, then we recover the chi-0 that the experimentalists defined in their work. Okay? So here's the results that we got for the integrated Raman response. This work was done in collaboration again with Helena Bragança, now with Indra Nilpol, and again with Marcello Civelli. These are our results for the Raman response as a function of the chemical potential. So when we change doping here, we decrease doping going from blue to pink over here. We decrease doping and we increase the chemical potential. And we can see that in our theoretical results, we have this non-monotonic behavior in agreement with the experiments. More than this, we see that we have a jump, so the transition between Fermi liquid to a pseudo gap. In the Fermi liquid, the Fermi surface is electron-like. In the pseudo gap, the Fermi surface is Hole-like, as I showed to you before. And when we have this transition, we have a discontinuous here. This all was for large values of U. So in the bottom here, we have U equal to 8, which is up here in this phase diagram. It's not in the phase diagram, but we have a transition from a pseudo gap to a correlated Fermi metal. If we now look at what happens at smaller values of U, we choose U equal to 3.5. The Fermi liquid is the ground state of the system, and as we change mu, or the doping, right, we see a continuous transition between the electron Fermi surface to a Hole-like Fermi surface. So for small values of U, down here in the phase diagram, we have a continuous transition, Lifshitz transition, and for large values of U, we have a discontinuous transition. So it's a change in the nature of the transition that we see, and we understand these results. I mean, we think that it is very important the fact that in case of large values of U, we have the pseudo-gap phase. So the pseudo-gap phase is the phase that is causing this change in the behavior from a continuous transition to a discontinuous transition. This is for the integrated Raman response. If we go back and look into a simpler quantity, which is the local density of states at the firm level, we see qualitatively the same behavior. So for small values of U, we have a continuous transition, and for large values of U, we have a discontinuous transition. In the insets, we see the dependence of the doping as a function of the chemical potential. We also see a discontinuity over here for large values of U. Okay, so I was talking about the pseudogap phase. Now I will start talking about the charge density wave. The pseudogap phase is more studied in the literature. The charge density wave is less studied, and we will explore this a bit now. Again, I start by showing experimental results. So this is the Raman response at the B2D channel. The B1D channel is dominated by the pseudogap phase. So that's why here we are looking at the B2D channel. So here are the Raman response as a function of frequency. We have many temperatures here. Let's look into 2 of them at least. The smallest one in temperature corresponds to this red line here. It's 120 Kelvin. In our scat here, this corresponds to this dashed line here in blue. And let's compare its behavior, the one in red, with the one in black. The one in black was obtained at 290 Kelvin. In the phase diagram, temperature as a function of doping, 290 Kelvin corresponds to this square over here. We do not have the CDW anymore, and it is close to the region where the pseudogap phase ends. So going back to this figure, so the black one corresponds to the dashed line over here, and the black curve corresponds to this continuous curve over here. What the experimentalists did was to take the difference between these 2 curves, and they got this, a deep hump feature, right? If we look at what they got from the experiments, we can see for different temperatures here, this deep hump feature. And they argue, they claim that this deep hump feature is a signature of the CDW phase in the B2D Raman response. They went beyond, it's hard to get the energy scale corresponds to this CDW phase, so they claim that it's related to the maximum of this hump here. So if they get the maximum of this hump, this was for a given doping, they analyzed other dopings as well, and they built this plot here, the energy scale as a function of doping. For the CDW, they were looking at the B2D response. They got these blue symbols over here. And when they look at it to the B1D response, they got the energy scales for the pseudogap and the superconducting phases, which corresponds to this black is pseudogap and red the superconducting energy scale. Okay, what we did theoretically, so of course we could start from a microscope model, but it was difficult to do it with the cluster DMFT code that we used in the previous works. So we used a phenomenological model. This is the Hamiltonian to describe only the CDW part. So we have a hopping term over here. We consider hopping up to 4 neighbors. And the second term corresponds to the CDW, which has a wave vector k. And k is equal to 2 times pi over NA. And we take n to be equal to 4 according to the experiments that I showed in my first or second slide. Okay, we can see over here that we have a modulation in charge corresponds to 4 times the lattice spacing. In this figure here, we have modulation only in the x direction, but in the model we have it also in the y direction. But we also want to describe the pseudogap phase. it is related to these ARBS measurements over here that I showed you before. And to describe the pseudo-gap phase, we use the Yang-Zhang-Rice ansatz. So it corresponds to writing this Green's function for the pseudo-gap phase. So there is a self-energy here, which is proportional to this capital delta PG here, which has this symmetry in K, and for a given value of doping, this amplitude here is fixed. But we want to put the two things together, the CDW and the pseudo-gap phase. To do so, we introduce auxiliary fermions, these F fermions here that live in this top plane. So the bottom plane is the same that I showed before. It is related to the C electrons. We describe the CDW phase. And then now we have these auxiliary fermions that really, they do not exist. So at some point, we will integrate out them. But it's the way to describe the pseudo-gap phase. There is a hybridization between C electrons and F electrons. This hybridization here between the C electrons and the F electrons. With this Hamiltonian here, the Green's function is written in this way. So we have some contribution from the CDW and the contribution from the pseudo-gap phase coming from the Yang-Zhang-Rice ansatz. Okay, here are the results that we got for the Raman response. This work was done by Moalisson Cavalcante, who is here in the audience. He was my PhD student. That's when we did this work. It was done in collaboration with Sumen Brag, Indra Nilpol, Alan Sakuto, who is the leader of the Raman group there in Paris, and Marcello Tivelli again. So let's look first for the Raman response for the B1G polarization as a function of energy. We will see that this Raman response is dominated by the pseudo-gap. How we do see here, let me define what the curves are. So black is a fermoliquid, blue is only the CDW, orange is only the PG, and green, it's when we consider both the CDW and the PG. And we can see that the green curve is dominated by the orange curve, which corresponds to the pseudo-gap. Now let's look at the Raman response for the B2D polarization of light. We can see that it is much smaller than the one for the B1G, but now the situation is less clear here who dominates. We did the same trick as the experimentalists did, so I already explained what the experimentalists did. We did the same thing. We did a difference between two curves in the last plots, right? The reference now is the fermoliquid, so we subtracted the fermoliquid result, where we do not have the pseudo-gap and we do not have the CDW, right? And we can see that this difference in the Raman response as a function of energy, we see that there is this deep hump feature, which was seen in the experiments. So our theoretical results are in agreement with the experiments. So we also calculate the energy scale here. So this is the same experimental results that I showed before, just now they are in electron volts, and we have only the results for the pseudo-gap phase and the CDW. What we did theoretically was to consider that the pseudo-gap has a dependency in the doping. So this was the dependency in K that we had before. Before this delta was fixed, now we consider a dependency with the doping in a way to reproduce what we have in the phase diagram, right? Is the dependency of doping here follows a dome. For the CDW, we keep the amplitude of it as fixed. And here are the results that we got for the energy scale as a function of doping. The one here in green corresponds to the pseudo-gap, and the one in red for the CDW. We do not get something related to what we have in the pseudo-gap in the phase diagram, so we do not have a dome dependency with doping for the energy scale. We have that it follows the one of the pseudo-gap. So Moalisson did this sketch over here, and the conclusion is that the pseudo-gap energy scale dependency with doping guides that of the CDW. So come to my conclusion is conclusive slides. I'm summarizing here the results we got for the Raman response. So in the first work, we considered a microscope model, the Hubbard model. And here's the main results that we got. This is the integrated Raman response in the B1G polarization of light. So the Raman response as a function of the chemical potential. If we increase the chemical potential, we decrease the doping. For small values of U, the electron-electron interaction, the system is always in a fermi-liquid phase, and we see a continuous transition. With transition, the Lifshitz one, where the firm surface changes from electron-like to Hole-like. When we increase U, that's the region that is relevant for cuprates, then we see that the system goes from a fermi-liquid with electron-firm surface to a pseudo-gap with wholly firm surface, and this transition becomes discontinuous. Here we also see that we have some symmetry around this doping at which the transition happens, while here we have an asymmetric behavior. And in the last part of the talk, I talked about a phenomenological model to describe the charge density wave. And here are the results we got. This is a change in the Raman response. Now at the V2G channel, that's where we can see signatures of the CDW phase. So it's a change in the Raman response as a function of frequency, and we see a deep hump feature in accordance with the experiments. We also calculate the energy scale as a function of doping, and the dependence of the energy scale for the CDW phase follows that of the pseudo-gap phase. So thanks for your attention.
Thank you very much, Maria Carolina, for the very nice talk. Do we have questions? So maybe I can start to break the ice. So in the first part of your talk, when you show the phase diagram and the continuous versus discontinuous transition, I was curious in the low U regime that you have these two regions where you have both hole and electron type pockets. So what changes if I go from 1 to 2, 2 to 3, and then 3 to 4? Like, I think mostly my question is, what is the difference between region 3 and region 4 in the low U?
I think the difference is that here we have the pseudo-gap phase, which has a slight, the correlated firm metal has smallest energy. The pseudo-gap phase is a bit up in energy, so the ground state is the correlated firm metal, and but we have this coincidence, this coexistence only in 2 and 3, not in 4. In 4, we only have the correlated firm metal, but the pseudo-gap phase becomes stable here in region 1. So when we move up in U, the pseudo-gap phase becomes the stable one, the ground state, and this one, there's not pseudo-gap phase here anymore. There's one thing that we can note here is the pseudo-gap phase always has hole-like firm surface. And this one has electron-like firm surface, so there shouldn't be the pseudo-gap phase there.
Thank you.
I don't know, I hope it...
Yes.
Thank you. So, but in this gray pseudo-gap region,
Yes?
what are the spins doing? Are they forming a spin liquid, or?
No, we had this, we map it into this cluster of sites, right? Am I going to the right direction here? And there are some fluctuations in the spin, but not a spin liquid. I mean, there are, I think, antiferromagnetic correlations between the spins.
Right. So, but you know, at 0 temperature, they have to form some kind of unique ground state, right?
Some kind of what? Sorry.
Unique ground state, right?
Yes.
And you have to have like a count of carriers that is only the holes that you have added to the antiferromagnet. So some, you know, the electrons that were essentially making the antiferromagnet must be doing something, right? So what is that state that they are forming?
Yeah, well, we were not plotting these quantities, so yes.
Must be a spin liquid, right? Because what else? Unless they are still antiferromagnetically ordered. But they
Yeah,
are not, right?
we start from the MOT phase here. We have where we have antiferromagnetic ordering, right?
Yeah. But the order is lost, right? There is no long range order in that gray region. So
Okay.
must be a spin liquid, right? You cannot tell what it is, right? From
Yeah,
your
we
method.
didn't plot the quantities to look into this. Yes.
Okay.
In the gray regime, we have something like this. Okay.
More questions? We still have a couple of minutes. Oops. Okay, I'll arrive there. Quickly as possible.
Carolina, obrigado. Thank you for the talk. So my question is regarding, maybe it's a bit more practical. So regarding the susceptibility calculations, you do compute the quantities all in the metrobarrier space, right? Frequency axis. So how do you do the analytical continuation to get the Raman susceptibilities? Because that's quite something
Indeed, we can
subtle
do
for the DMFT, right?
We can do the calculation in both axes, right? The problem is that in the real axis, we have to add some broadening, right, to avoid divergences of the Green's function. And then the results, depending a bit on this doping, I mean, it's more sensitive, it is sensitive to it. To try to avoid this sensitive to the broadening, then I was looking at I was concentrating on the imaginary axis calculation. But since I was showing you, especially in this Raman response data here, I was showing you results close to the energy. There should be a coincidence between the two calculations. But I did do the calculation on the imaginary axis and on the real axis. We can do this because it's a zero temperature calculation, so we can get both. But the calculation is more stable on the imaginary axis, and on the real axis, it depends on this broadening that we add. So we decide to show the results coming from the imaginary axis, because then it does not depend on this broadening that we add.
I see. It's just that I'm confused, because if we go back to the equation where there is the integral over frequency of the susceptibility, the integral is is on the real axis, right? So in principle, I would say that
you mean this one?
No, the other one. So this is on the imaginary frequency. I get it.
Well, I can write either on the
Raman.
imaginary axis or the real axis, this expression,
I'm not talking
right?
about this equation, I'm sorry. It's about the equation for the Raman scattering, which is the integral of the imaginary part of the susceptibility. That
no, it's not the integral of the imaginary one. It's the integral of the real one.
Okay.
This equation,
and then when
this is a Hilbert transform when we go from real axis to imaginary axis, right?
I see.
This was the one that they used experimentally. This is the quantity that they really measure, and they divided it by omega and integrated it in omega up to a cutoff. And they got this quantity over here. This is what they got from the experiments, right? But in my calculation, I was saying I was doing on the imaginary axis. This is the quantity here. But always we can relate the quantities on the imaginary or anywhere we want. We can write this equation here, which corresponds to Kramer's chronic, right?
I see. Thank you. I'm sorry for the confusion.
Yeah, no. No problem.
So I think we need to move on. Let's thank Maria Carolina again. So our next speaker